Hello and welcome back. We are starting chapter 4 today. This lesson is going to be quite long. You will need a calculator for sure with this one. Make sure that you practice when I'm practicing. And we're going to be talking about probability. This is the longest chapter that we'll be running into. Part 1 is just sort of an introduction to a few different types of probabilities, and then parts 2, 3, and 4 are different lessons, and they go into other places. So we're going to go ahead and jump into it. In probability and experiment, is any process with uncertain results that can be repeated. And that's important. It has to be repeatable. In the short term, results are uncertain, but in the long term, the proportion in which a certain outcome is observed can tell us quite accurately the probability of that outcome. And next up is this law of large numbers. Here's the idea. What I do with my regular classes is I'll pull out a coin and I will flip it 10 times and I will write down heads or tails. And let's say I did that and I got that 7 were heads and 3 were tails. Well, that means 70% of the time it was heads. Now we know that it should be 50% of the time. So what I then do is have the students pull out coins and they all flip it 10 times. And then we write the results on the board as far as how many heads or tails, and then average all of those, and it's much, much closer to 50%. So the idea is the more an experiment is done, the closer and closer you're getting to the true probability or mean or standard deviation or whatever it is that we're looking for. We have a few definitions to get through. And the first one is a sample space. A sample space S of a probability experiment is the collection of all possible outcomes. So for example, and I'm being very binary here, so I apologize for that, but when there are two kids, the possibilities are girl-girl, a girl and a girl. Possibility is a boy and a girl. Possibility is a girl and then a boy. And possible that it's 2 boys. This is the complete sample space. And once again, I understand I'm being quite binary here, so non-binary, please pardon me. But for what we're doing here, this is much easier to go through. So 4 possibilities in having 2 kids. And notice the order matters. If I had a die, like one die that I rolled, my sample space is, I could roll a 1, a 2, a 3, a 4, a 5, or a 6. And that is my entire sample space. We'll talk more about that here in just a second. An event is any collection of outcomes from a probability experiment. Events may consist of one outcome or more than one outcome. We often use capital letters such as E, F, and G to represent events. And again, these definitions won't make a lot of sense till we start using them. Number 3, an unusual event is an event that has a low probability, typically less than 5% of occurring. We talked about that in a different lecture in chapter 3. A probability model lists the possible outcomes of a probability experiment and each outcome's probability. And again, these are just words we'll be using. They'll make more sense when we start actually using them. So rules of probability. Probabilities are always between 0 and 1. So if you're ever running and you get a probability of 1.3, that for sure is not right. It's got to be something between 0 and 1. If an event is impossible, then the probability of the event is 0. Notice we're including the endpoints, the equals. If an event is a certainty, the probability of the event is 1, or 100%. Meaning if I decide to drop this pen 1,000 times, 100% of the time it's going to drop to the ground, or to the table. Or, for example, an impossible event like a human being can't actually walk on water without some sort of trickery. Next up, practice just a little bit. The probability that an individual walks to work is 0.025. Notice that's between 0 and 1. This means if we survey 100 people, about 2.5 of them will walk to work. Now, there's no such thing as a 0.5 person, obviously. This would mean that I would expect there to be 2 or 3 that walk to there. Again, assuming this is a true probability. Oh, let me take that off. Good. All right, so we are going to draw something called a tree diagram. Using a tree diagram to describe the sample space and the fundamental counting rule. If a basketball player shoots three free throws, describe the sample space of possible outcomes using S for the made free throw and F for not, meaning success or failure. So for the first shot, they could be successful or they could have failed. They could have made the shot or not made the shot. Next shot, I should say, is successful or it's fail. And next up, we have success or fail again. So we end up with our sample space. Looks like this. Success, success, success. Success, success, failure. Success, failure, success. Success, failure, failure. Failure, success, success. Failure, success, failure. Failure, failure, success. And failure, failure, failure. There's the entire sample space. First we used a tree diagram, and then we wrote out our sample space. And what's the size of the sample space? 1, 2, 3, 4, 5, 6, 7, 8. The size is 8. And when we say size, that often means that we're using the letter N to represent our sample size. If a person rolls a 4-sided die and then flips a coin, describe the sample space using 1, 2, and 3, and 4 for the die outcomes, and H and T for the coin outcomes. So let's do a tree diagram again. So roll the dice. We can get a 1, a 2, a 3, or a 4. Then we flip a coin. We either get heads or we get tails. So it looks like this. We roll a 1 and we get a heads. We roll a 1, we get a tails. Roll a 2, we get a heads. 2, we get a tail. 3, we get a heads. Or 3, we get a tail. 4 heads. And 4 with a tail. So again, our sample size is 1, 2, 3, 4, 5, 6, 7, 8. That's a coincidence. They both happen to be 8. That's not always 8, of course. All right, and here, so we have 3 methods to approach this. This is the bad one. This is the one we don't want. This is the one most people normally do, unfortunately. It's not a very scientific way of doing it. All right, so the way that we find a probability is the frequency that the event happens over the total number of trials within an experiment. And you've used this before. This isn't terribly new. Like when you have a math test and you get a 25 out of 30 to get the percent, you just divide that out. That's the probability. What is the probability that, in a survey of 1,100 female adults, it was determined that 341 volunteered at least once in the past year. So the probability of volunteering is 341 over 100. Meaning of these women, if we randomly selected one, what's the probability that we selected one that volunteered within the last year? It's going to be whatever that is. We can even get a decimal approximation for that. 3.1, yep, I'm missing a 1, 1100. So 31%, or 0.31. What is the probability that a randomly selected adult female volunteered at least once in the past year? Well, actually, I just did that here. So this is actually part A. Interpret this probability. So if, oops, make sure you can see that. If a survey of 100 females, about 31 of them volunteered at least once last year. That would be our interpretation. We are moving on. All right, next up. A survey of 500 randomly selected high school students determined that 288 played organized sports. What is the probability that a randomly selected high school student plays organized sports? So, probability that they play sports, it's going to be 288 out of 500. Or 0.576. Now, for some of these examples, we'll leave them as fractions. Sometimes they'll be decimals, sometimes they'll be rounded decimals, sometimes they'll be percents. It just depends. So, computing the probability using the classical method, we're going to get the number of ways for E to occur. Over the total number of outcomes. And that's the number of E over the number of S. So the other one was probabilities, this one's are number counting. They basically mean the same thing. All right, practice. So we have a sample space S of 1 through 7. Compute the probability of an event answer as an integer or a simplified fraction. So they don't want a decimal answer for this one. That E is an odd number. Now, my denominators for all of these are going to be 7. Because that's the sample space. Now, that E is an odd number. How many odd numbers do we have? We have 1, 2, 3, 4 of them. So here's the probability of F being an even number less than 6. So it doesn't say less than or equal to 6, so here's 6, an even number that's 4, and so there's 2 of them. All right, probability of G. A number less than 10. How many of these numbers are less than 10? All of them are. Meaning if I randomly select any of these numbers, 100% of them will be less than 10. And probability of A. Now, how many of them are multiple of 3 or an even number? So I'm going to do this. I'm going to green underline the multiples of 3. And I'm going to overstrike the even numbers. Now, you can see that's going to be a total of 1, 2, 3. Now here, this one's double counted, so that's only 4. So we don't want to count it twice. We're going to approach that idea of the double counting here in just a minute. Again, this is the red and the greens, but for 6 we have overlap. And once again, we'll come back to that. Here we have 2 dice being rolled, and these are all the possibilities. In fact, there are 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5, 6. So there are a total of 36 outcomes. That's going to be my denominator each time. Compute the probability of rolling a 7. Here's a 7. 1, 2, 3, 4, 5, 6. So the probability of a 7, there are 6 possibilities out of 36, or 1 out of 6. Part B, probability of rolling snake eyes. Snake eyes means a 1 and a 1. Well, that's 1 out of 36. Very low probability. Let's interpret this for a second. So 1 divided by 6. That means about 17% of the time, I'm going to roll a 7. About 2.8% of the time, I'm going to roll snake eyes. So that's quite a low probability. Oh, that's kind of a glare there. There we go. All right, next up. Oh, too high. There we go. Once again, this question is quite binary, so my apologies. Compute the probability of having exactly 2 boys in a 3-child family using the classical method, assuming the boys and girls are equally likely. So I'm going to do a tree diagram. So it looks like we have 3 boys. So this is the entire sample space. I was just doing this by going boy, 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 girl, boy, girl, boy, boy, girl, girl, and so on. So that makes up the sample space for us. So exactly 2 boys. Notice it says exactly. So this doesn't count. The 3 boys doesn't count. So probability of 2 boys. Well, my denominator is going to be 8. And how many sets of 2 boys? 1, 2, 3. So there's a 3 out of 8 chances that of three children, exactly 2 will be boys. Next up, subjective probability. This is when someone says, it's got to be 90% of the people agree with me. It's statements like that where we all just kind of go, you know what, you're just making that number up. That's exactly what subjective probability is. It's what we try to avoid doing in any experiment. That can rarely turn out well. Complement rule. So the complement means it's whatever's left over from the 100%. So can you see we have 2 different notations for it. We have E bar, and then sometimes, yeah, they do E to the C power, it looks like. They both mean the same thing. Now, there's 2 other ways we can write this. This is the probability of E equals 1 minus the probability of the complement of E. So these both say the same thing. Now, you actually use this logic all the time. If I say I'm in a room and 40% of the people in there are men, how many of them are women? Well, you just do 100 minus 40 and you get your 60%. So we use this logic all the time. All right, because of probability and its complement always add up to 100% or 1. So find the complement. I'm going to use the bar notation. Well, we know that P of E is 0.29, so the complement is going to be 1 minus 0.29, or 0.71. A bag of candy consists of 4 flavors, 80 lemon, 35 grape, 25 cherry, and 20 blueberry. If a candy is chosen at random, what is the probability it is not blueberry? Now, when we have this not idea, not outcome, we can use the complement to do this. I could add up all the ones that are not blueberry, so the probability of not blueberry. Or I could do this. I could go 1 minus the probability of blueberry. It's the opposite. So we have a total, let's see, 80 plus 35 plus 25 plus 20. That's my denominator. And how many of them are blueberry? 20 are. Getting a common denominator. We are here. And that reduces to 7 over 8. Meaning there's a pretty good chance if I randomly select one of these, it's not going to be a blueberry. Number 3. The data represents the number of live multiple delivery births, 3 more babies, in women from ages 15 to 54. And first off, I need to get N, meaning I need to find out how many total women there are. So this is N of S. Is going to be adding all of these up. So let's do that. That's 92 plus 515 plus 1623 plus 2824 plus 1852 plus 373 plus 115. So I got 7394. So that's going to be my denominator for each of these questions. I also want to bring back the idea of a bell curve. Can you see most of the births are from ages 25 to 39? Meaning not a lot of teenagers are having children here, and a lot of people in their women in their 40s and 50s are not having children. So let's go ahead and get started. So a randomly selected woman between these ages having multiple births are being randomly selected. Determine the probabilities of each of these, and we're going to use a fraction here. So mother is from age 30 to 39. So that's these two categories here. So the probability of 30 to 39 is going to be 2824 plus the 1852, again all over my common denominator up here, 7394. Do you see where I'm getting these numbers from? 30 to 39, we're here. So I have to add those up. 2824 plus. Again, you should be doing this with your calculator. Don't just watch me do it. And that might reduce, it does reduce, but I'm going to leave it. So here we have the mother is not. So again, what I could do is add up all the ones that aren't, but I may as well use this and its complement. Getting a common denominator here. There we are. So again, I hope that you can track coming up with a common denominator and so on. The mother is less than 45 years old. So I'm going to say the mother is less than 45 is going to equal the complement of the probability of bigger than or equal to 45. It's going to make it a little bit easier. And how many of them are bigger than or equal to 45? Well, that's only 115 there. So this is going to be 1 minus 115 over the 7394. Again, if I needed to, I could add all those up, but I think it's just going to be easier to subtract the 115. So 7394 minus 115. And once again, if you were to add up all of these except that last one, we would get exactly this. Feel free to verify that, please. So here's another one. The mother is at least 20 years old. For D. At least 20 means all of these, or again, I can do the complement. And finally, the mother is less than 20 or greater than 44. So less than 20 is going to be the 92. Bigger than 44 is 115. We could do a complement with those as well, but this is small enough, doesn't matter. So this is one use of it. So often when you're excluding something, so how many of them are not this or something like that, you'll use the complement rule. And we'll use the complement rule throughout the rest of the semester. That's just going to be a normal part of it. Last page, part 1. So if you don't know playing cards, you may want to learn a little bit about it. Let me go ahead and talk about it just a little bit. There are four suits, they're called: clubs, diamonds, hearts, and spades. And to be clear, diamonds and hearts are of the color red. If this was in color, you'd be able to see it. And the clubs and spades are actually what are called black cards, red cards and black cards. And within each suit, there are 13 cards. The first card is called the ace. Then you go basically 1 through 10, and then after that you have the jack, queen, king. These are called face cards. It goes in that order, so this is like 11, 12, and 13, but we use that. So you can see half of the cards are red, half the cards are black. There's a total of 52 cards because there's 13 in each suit and 4 suits. 4 times 13 is 52. 52. And we're going to find probabilities. All right, red queens. Here are the queens. These 2 are red, so there's only 2 red queens out of 52. So the probability of randomly selecting a red queen is 2 out of 52. And it doesn't say how it wants the answer written, so I will leave it as an unreduced fraction. Face card. These are all face cards here. There's 3 by 4, so there's a total of 12 face cards out of 52. I'm going to keep everything the same denominator just to remind you that the denominator is always going to be 52 for now until it gets reduced. It's a diamond. So we're randomly selecting a card and it's a diamond. How many diamonds are there? Remember, there's 13 in each suit. The 2 of clubs. There is exactly 1 2 of clubs. That it's a black card. How many black cards are there? There's 13 and 13. That's 26 out of 52. And a green card, none of these are green. So this has a probability of 0. Or you could say 0 out of 52 to keep the denominator the same. Whew, we made it. So that's the end of section 1.